Good morning, students. In the previous class, that is class 1 of the chapter electrochemistry, I completed, that is introduction part. What do you mean by electrochemistry? What is conductor, non-conductor or insulator? What is electrolyte, non-electrolyte, weak electrolyte, strong electrolyte? What do you mean by degree of dissociation? What is electrolysis? What is the process of electrolysis? And what is a preferential discharge theory and the application of a preferential discharge theory? Today, in class 2 of the chapter electrochemistry, I will try to complete the Faraday laws of electrolysis, that is Faraday first law of electrolysis and the second law of electrolysis and some of application of Faraday law. So before going to the today class, that is the Faraday laws of electrolysis, let us discuss a little bit idea about the previous class. That is the most important thing is that preferential discharge theory. What is this theory? This theory states that when more than one type of ion are present in electrolyte during electrolysis, then that ion migrate to their respective electrodes which possess least chemical energy and more deposition potential, or which possess least discharge energy and more deposition potential. In other words also, this theory may be stated as when more than one type of ions are moved towards a particular electrode, then in case of cation, that one stronger oxidizing agent get preferred move to the cathode. Similarly, in case of anion, that one the stronger reducing agent get preferred to get at the anode. On the basing upon this one, for cation, increasing order of deposition potential is there in form of a series, and for also an anion, this is known as activity series. So let us recap for cation, that is potassium, calcium, sodium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, silver and gold. This is known as increasing order of deposition tendency, deposition potential for cation. Similarly, for anion, that is sulfate, nitrate, hydroxide, chloride, bromide, iodide. This one is the increasing order of deposition potential. Deposition potential. The most important thing is that the deposition potential of an ion also depends upon the concentration of the solution, concentration of the electrolyte, and also the nature of the electrode, whether it is attackable or non-attackable. Let us discuss this one by giving one example. For example, mark that. Predict the product of electrolysis. Predict the product of electrolysis. It is a 2-mark question. What is the question? That is aqueous solution of sodium chloride by using platinum electrode. By using non-attackable electrode. It is a 2-mark question. Question is That is sodium chloride solution. Aqueous solution of sodium chloride undergoes electrolysis by using platinum electrode. Predict the product. What happened at cathode? What happened at anode? Mark that. So sodium chloride on electrolysis break down to Na plus Cl minus, H2O break down to H plus OH minus. So mark that. Two type of cation is there, Na plus and H plus. H plus higher deposition potential. So what happened? At cathode, H plus electron give rise to H, that is known as primary change. H plus H give rise to H2, that is known as secondary change. At cathode, hydrogen gas is liberated. At anode, mark that, Cl minus is there, OH minus is there. So Cl minus higher deposition potential. So Cl minus electron give rise to Cl, that is known as a primary change. And Cl plus Cl give rise to Cl2, it is known as secondary change. Mark that. It is the predict. So from this it is clear that during electrolysis of aqueous solution of sodium chloride, hydrogen gas is liberated at the cathode while chlorine gas is liberated at the anode. Same question is there, same data is there, but different question. Another type of question is there. What is the, in this case, predict the pH of the solution. What is the pH of this resulting solution after electrolysis? So observe that what type of ion is left behind after electrolysis. Na plus ion is left behind and OH minus ion is left behind. That means the solution is basic in nature, so pH greater than 7. Another type of question is there, mark that. So during electrolysis of aqueous solution of sodium chloride, if solution is very dilute, mark that, another type of question. If sodium chloride solution is very dilute, then what happens? Mark that. That means we already discussed that is deposition potential of an ion also depends upon the concentration. So since it is very dilute, concentration of Cl minus is very low. In that case, instead of chlorine at anode, what happened? OH minus electron give rise to OH, it is known as a primary change. 4OH give rise to 2H2O plus O2, it is known as secondary change. So from this it is clear that the deposition potential of an ion not only depends upon this preferential theory but also depends upon the concentration of the electrolyte and also the nature of the electrode, whether it is attackable or non-attackable. So today in class 2 of the chapter electrochemistry, now switch over to the first long question of this chapter, that is Faraday laws of electrolysis. The Michael Faraday gave 2 laws on the basis of electrolysis, and according to his name, that is known as Faraday's first law of electrolysis and Faraday's second law of electrolysis. Let us discuss one by one. First is Faraday's first law of electrolysis. First we discuss Faraday's first law of electrolysis. This law states that the mass of the substance deposited or liberated at their respective electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. I repeat again. This law states that the mass of the substances get deposited or liberated. If it is solid, deposited; if it is gaseous, liberated at their respective electrodes during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. Mark that. What is the statement? This law states that the mass of the substance get deposited or liberated during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. That is, the mass of the substance get deposited or liberated during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. Next, we go through its description, mathematical expression part. Mathematical expression. Let W is equal to quantity of W is equal to mass of the substance get deposited during electrolysis and Q is equal to the quantity of electricity. Q is the quantity of electricity passed through the electrolyte. Mark that. Let W is the mass of the substance get deposited or liberated at their respective electrode during electrolysis, and Q is the quantity of electricity passed through the electrolyte. Then, according to this law, W directly proportional to Q. Then, according to this law, W proportional to Q. Again, we know that Q is equal to IT. That is I, amount of current in ampere, T, time per second. Again, we know that Q is equal to I into T, where I is equal to amount of current or quantity of current in ampere, T time in second. So putting this value of a Q from equation 2 in equation 1, we have that is W proportional to I into T, or W is equal to Z I T, equation 3, where Z is a proportionality constant. Z is a proportionality constant which is known as electrochemical equivalent, that is ECE, where Z is a proportionality constant which is known as electrochemical equivalent or ECE. Next, it is our duty to make a definition for ECE or Z. Mark that. So from this relationship, mark that if I is equal to 1 ampere, T is equal to 1 second, then Z is equal to W. Mark that. If I is equal to 1 ampere and T is equal to 1 second, then W is equal to Z. So from this relation, one is able to define Z, that is electrochemical equivalent of a substance is defined as the mass of substance deposited or liberated at their respective electrode during electrolysis when 1 ampere of current passed for 1 second. Mark that. Hence ECE, electrochemical equivalent of a substance, is defined as the mass of substance deposited during electrolysis when 1 ampere of current passed for 1 second. In other words, also mark that electrochemical equivalent of a substance is defined as mass of the substance deposited during electrolysis when 1 coulomb of electricity passed through the electrolyte. So from this definition, so it is clear that from the previous relation we know that W is equal to ZIT or Z is equal to W by IT. It is one relation. Mathematical expression for Z is equal to W by IT. Next, we know that unit of a charge, that is coulomb. 1 coulomb is equal to 1 ampere into 1 second. Another bigger unit of coulomb charge is there, that is known as a Faraday. According to Michael Faraday, that is known as a Faraday. That is 1 Faraday is equal to 96500 coulomb. The bigger unit of charge, that is Faraday, 1 Faraday is equal to 96500 coulomb. It has been observed that By the passage of 1 Faraday of electricity, the amount of substance deposited is equivalent to 1 gram equivalent. I repeat again. It has been observed that by the passage of 1 Faraday, that is 96500 coulomb quantity of electricity, the amount of substance get deposited is equal to 1 gram equivalent. Mark that. It has been observed that by the passage of 1 Faraday, that is 96500 coulomb quantity of electricity, the amount of substance get deposited is equal to 1 gram equivalent. By the passage of 96500 coulomb quantity of electricity, amount of substance deposited is equal to 1 gram equivalent. Therefore, the amount of substance deposited by the passage of 1 coulomb of charge, 1 coulomb of electricity, the amount of substance deposited is equal to 1 gram equivalent divided by 96500. By passage of 96500 coulomb, mass deposited 1 gram equivalent. By passage of 1 coulomb, mass deposited is equal to 1 gram equivalent by 96500. That is equal to ECE. This one is equal to electrochemical equivalent, or Z is equal to gram equivalent, otherwise it is also known as chemical equivalent by 96500. That means Z is equal to chemical equivalent, C.E, chemical equivalent by 96500. Chemical equivalent, otherwise also known as equivalent mass. That means Z is equal to E by 96500. Another one definition, mark that. Another one mathematical relation for Z also, that is Z is equal to E by 96500. What is E? E is known as equivalent mass. E is known as equivalent mass is equal to chemical equivalent is equal to equivalent mass is equal to atomic mass by valency. So mark that. First relationship, that is Z is equal to W by IT. Second relationship, Z is equal to E by 96500, where E is known as equivalent mass. Equivalent mass also is equal to atomic mass by valence. So putting this data, this relation also we can write, mark that. W is equal to ZIT, Z is equal to E by 96500 into I into T. Again E is equal to atomic mass by valency into I into T by 96500. This one is equal to W. This is the final mathematical expression. Mark that. How many term unknown term? 1, 2, 3, 4, 5. 5 terms are there in problem while going to solving problem. 4 data is given. We have to find out the last one. So before going to solving the problem, another 2 to 3 points we have to remember under the heading of a note. That is, again I write here, W is equal to atomic mass by valency into I into T by 96500. So before going to the problem, note that is the charge of one electron. 3 to 4 points are necessary. Charge of an electron. Charge of an electron is equal to 1.6 into 10 to the power minus 19 coulomb. Point 2. Charge on 1 mole of electron is equal to 1.6 into 10 to the power minus 19 into 6.023 into 10 to the power 23 coulomb, nearly equal to 96500 coulomb, or nearly equal to 1 Faraday. Charge of 1 electron is 1.6 10 to the power minus 19 coulomb. Charge of 1 mole or Avogadro number of electrons nearly equal to 96500 coulomb or 1 Faraday. Next point. The number of electrons present in 1 coulomb is equal to 6.25 into 10 to the power 18 electrons. Next is metals are good conductor of electricity than that of strong electrolyte. Conductor are of 2 types, already covered in class 1. Conductor are of 2 types. One is a metallic conductor, one is electrolytic conductor. So metallic conductor, metals are good conductor than the electrolyte. In metal, the important one is the free electron. Mobile electron plays an important role. In electrolyte, the ions, cation and anions. That means from this it is clear that the electrons move faster in metal than that of the free ions. Next point. The electrons present in metal move faster than that of ions, means cations and anions present in the electrolyte. These are some important points necessary for solving some problem. So let us solve 1 or 2 problems basing upon this formula. Mark that. Again I repeat. 1, 2, 3, 4, 5. 5 parameters are there unknown. 4 are given in the question. We have to identify the last one or fifth one. For example, question: when 0.25 ampere of current is passed through copper sulfate solution for 30 minutes. Copper sulfate solution for 30 minutes. Calculate the mass of copper get deposited. Mark the question. What are the data given? Answer. Given. What are the data given? That is I is equal to 0.25 ampere given. So passed for 30 minutes given. T is equal to 30 minutes. That is 30 into 60. This much. Most one important thing is that only in electrochemistry in Faraday law, while solving the problem, the time may mean second, minute, hour, day or year, whatever may be. Our aim is to always transfer the time in second. Remember that while solving only in electrochemistry Faraday law, time must be converted into in second. So mark that. I given, T given. Next, copper sulfate solution. Another 2 factor is there. So one thing is there, may given or not, we have to remember that is atomic mass of copper is equal to 63.5. Sometimes it may given or not, we have to remember. So mark that. Atomic mass 63.5 given. Copper sulfate, so CuSO4, from this it is clear that valency of copper is 2. So mark that. Atomic mass given, valency given, current given, time given. So 1, 2, 3, 4 parameter given. Can we calculate W? Very simple. Putting this formula, that means W is equal to 63.5 by 2 into 0.25 into 1800 by 96500. By solving this one, mass of copper deposited during electrolysis can be calculated. Move to another type of problem. Mark that. Problem number 2. When 0.15 ampere of current is passed through a metal salt solution for 1 hour. For 1 hour, 0.735 gram of metal deposited. Calculate the valency of that metal. Data given. Atomic mass of that metal is 1 and 2. Read the question, answer. What are the data given? 0.15 ampere, I is equal to 0.15 ampere. Through a metal salt solution for 1 hour, T is equal to 1 hour, that is 3600 second. Then what happened? This much mass is deposited, that is W is equal to 0.735 gram. And data is given, atomic mass is given, that is atomic mass is equal to 112. Question is calculate valence. Mark that. From the 5 parameter, 1, 2, 3, 4 parameter are given. So putting this value, that is valency. We know that valency is equal to atomic mass into I into T divided by weight into 96500. Mark that. Atomic mass given, current given, time given, weight given, 96500 given. By solving this one, we have to find out the valency. One important thing that while solving the problem, the data may be in a fraction or decimal. Suppose by solving this problem, it is maybe 2.1, 2.01, 2.02. If this one, as valency is a pure whole number, we have to round off is 2. Suppose 2.99, 2.9, then round off to 3. Because valency neither decimal nor fraction, it is a whole number. This is little idea how we apply this problem, that is W is equal to ZIT. Next we switch over to another some type of problem relating to Faraday's first law. We know that one relationship that Z is equal to E by 96500, where E is known as atomic mass by valency. So basing upon this one problem is there. Question: calculate ECE of zinc. Question is calculate atomic electrochemical equivalent of zinc. Given that atomic mass of zinc is 65, this data is given. So how is solved? Mark that. Very simple. Answer: given atomic mass of zinc is 65, we know valency of zinc is 2. That means atomic mass valency is given. Therefore, Z is equal to E by 96500 is equal to 65 by 2 into 1 by 96500. 65 2, that means equal to mass by valency, equal to my valency by this one. Solving this one, we can able to calculate the equivalent mass of zinc. Next we go to another type of problem. Calculate the charge in coulomb for the following oxidation or reduction. Point 1. 1 mole of aluminium ion to aluminium. Point 2. 1 mole of MnO4 minus 2 Mn2 plus. 1 mole of Cr2O7 2 minus 2 Cr3 plus. 1 mole of H2O2O2. 1 mole of ferrous oxide to ferric oxide. Mark that. These are the problem we have to solve. Answer bit 1. So this reaction may be a reduction, gain of electron, or oxidation, that is a loss of electron. We solve one by one. Mark that. 1 mole of L3 plus, that means it gain 3 electron, give rise to L. It is 1 mole. It is 3 mole. It is 1 mole. We know that charge on 1 mole of electron is equal to 1 Faraday, that is 96500 coulomb. Therefore, charge on 3 moles of electrons is equal to 3 into 96500 coulomb. Move to second one. Permanganate to manganese. So here manganese oxidation number +2. Our aim is to find out the oxidation number. We know how it is calculated in class 11. Let it's not known. Let the oxidation number is +x plus oxygen is -2 is equal to -1. So x is equal to -1 plus 8, that is +7. Here is +7. Here is +2. That means 5 electron. Mark that. It is 1 mole. It is 5 mole. Therefore, charge on 5 mole of electrons is equal to 5 into 96500 coulomb. Move to next one. Mark that. What is the next one? Next one is potassium, that is dichromate Cr2O7 bit 3, 2 minus 2 Cr3 plus. It is not known. Let it is 2x plus 7 into -2 is equal to -2. 2x is equal to -2 plus 14 is equal to +12. X is equal to +6. It is +6. 2 chromium is there, +12. It is +6. So +6 electron. Mark that. It is not known. Let it is x. So 2 chromium, 2x plus 7 into 1 oxygen. Oxidation number is -2. Equivalent to as it is an ion. So total sum of the oxidation number is equal to its charge. Solving x is +6. 2 chromium +12. It is +6. That means it is 1 mole, 6 mole. So therefore, charge is equal to 6 into 96500 coulomb. Next one, that is fourth. 1 mole of conversion of 1 mole of water to oxygen. Mark that. H2O transport to O2. We have to balance this equation by ion electron method. Mark that. Plus 2x plus 2 electron. That means 1 mole, it is 2 mole. Therefore, charge required 2 into 96500 coulomb. Move to next one. 1 mole of ferrous oxide to ferric oxide. Next one is 1 mole of ferrous oxide to ferric oxide. Mark that. Ferrous to ferric. Loses 2, loses 3 means loses another one is there. That is 1 mole. It is 1 mole. That means charge required 96500 coulomb. Next, move to another some type of problems. Calculate. Next, calculate the charge on bit 1 gram ion of N3 minus bit 2 1 gram N3 minus ion. Mark that. Seems to be similar to question, but there is a difference is there. It is 1 gram ion, it is 1 gram. Answer, mark that. Big one. Charge on N3 minus is equal to 3 into 1.6 into 10 to the power minus 19 coulomb. So charge on 1 nitride ion is equal to this much. So 1 gram ion means Avogadro 6.023 into 10 to the power 23 number of ions. So total charge required is equal to 6.023 into 10 to the power 23 into 3 into 1.6 into 10 to the power minus 19 coulomb. Move to next one. B2. What is the B2? That is 1 gram. We know that nitrogen, that is B2 answer. 14 gram of N3 minus ion contain Avogadro, that is 6.023 into 10 to the power 23 N3 minus ion. Then 1 gram N3 minus ion is equal to this much by 14. This much number of ion. Again, we know 1 N3 minus ion contain 3 into 1.6 into 10 to the power minus 19 coulomb. 1 nitrate ion contain this much charge. So this number of nitrate ion contain 3 into 1.6 into 10 to the power minus 19 into 6.023 into 10 to the power 23 divided by 14, this much coulomb. Move to another type of problem. Question number 7. When 1 ampere of current passed through acidified water for 1 hour, calculate the volume of hydrogen liberated. Mark that. Data is given. 1 ampere of current passed for 1 hour through acidified water. We have to calculate the volume liberated, volume of hydrogen liberated. So answer. The electrode reaction in case of acidified water, that is 2H plus electron give rise to H2. That means 1 mole is equivalent to 22.4 liter. This one is 2 mole, that is 2 into 96500 coulomb. That means from this data it is clear that by the passage of 2 into 96500 coulomb, the volume of hydrogen liberated 22400 ml. So by the passage of 1 coulomb, 22400 by 2 into 96500. So what is the data given? That is data given is I is equal to 1 ampere, T is equal to 1 hour, that is 3600 second. So Q is equal to 3600 coulomb. So by the passage of this much amount of coulomb, the volume is 22400 by 2 into 96500 into 3600. This much ml. Move to another type of problem. Calculate the charge required. Calculate the charge required for deposition of 20 gram of calcium from molten calcium chloride for complete oxidation of 90 gram of water. Answer bit 1. Mark that. Electrolysis of calcium chloride, that means breakdown to calcium ion give rise to calcium, that is 1 mole. 1 mole means 40 gram. It is 2 Faraday. 2 moles means 2 Faraday. That means for the deposition of 30 gram of calcium, charge required is equal to 2 into 96500 coulomb. So for the deposition of 20 gram of calcium is equal to 2 into 96500 coulomb by 2 is equal to 96500 coulomb. Move to second one. That is for complete oxidation of 90 gram of water. That is 90, water is 18, that is 5 mole. We know that in the previous problem, for complete oxidation of 1 mole of water, 2 Faraday is required. For complete oxidation of 1 mole of water, charge required is 2 Faraday. Therefore, for oxidation of 5 mole of water is equal to 2 Faraday into 5. These are some little idea relating to the application part of Faraday first law of electrolysis. So we move next. Switch over to the second law of electrolysis, that is known as the Faraday second law of electrolysis. Next is Faraday second law of electrolysis. This law states that when 2 or more electrolytic cells are connected in series and same quantity of electricity pass through them, then the amount of substance deposited or liberated at their respective electrode is directly proportional to their equivalent masses. Mark that. This law states that when 2 or more electrolytic cells are connected in series and same quantity of electricity is passed through them, then the quantity of substance deposited at their respective electrode is directly proportional to their equivalent masses. Mark that. This law states that when the same quantity of electricity passes through the different electrolyte connected in series, then the masses of substance deposited at their respective electrode is directly proportional to their equivalent masses. Mark that. So let us consider 3 electrolytic cells. One contains copper sulfate solution, one contains silver nitrate solution, one contains acidified water. 3 containers is there which are connected in series. First container contains copper sulfate solution. This is known as copper sulfate solution. It is known as silver nitrate solution. It is known as acidified water. Same quantity of electricity pass through them. Then what happens? If we take these 2 containers, then mass of copper deposited by mass of silver deposited, that is mass of copper deposited by mass of silver deposited, is equal to equivalent mass of copper by equivalent mass of silver. Mark that. Let us, W1 is the mass of copper deposited, W2 is the mass of silver deposited, E1 is the equivalent mass of copper, E2 is the equivalent mass of silver. Then applying this law, W1 by W2 is equal to E1 by E2. Similarly, by taking this second and third, mass of silver deposited by volume of hydrogen liberated is equivalent to equivalent mass of silver by equivalent mass of hydrogen. Suppose you call it these two. That is W1 by W2 is equal to E1 by E2. Dividing numerator denominator of the RHS by 96500, we have, mark that. W1 by W2 is equal to E1 by 96500 by E2 by 96500. We know the equivalent mass by 96500 is equal to electrochemical equivalent, that is Z, or W1 by W2 is equal to Z1 by Z2. It is one relation, equation 1. It is one relation, equation 2. So if we combine these two relations, then it is clear that what is the result? Combining equation 1 and 2, we have W1 by W2 is equal to E1 by E2 is equal to Z1 by Z2. It is the mathematical relation of Faraday second law of electrolysis.